Hello dear student, welcome to the next lecture in tensor analysis. This lecture is a continuation video for our previous lecture in tensor calculus. Therefore, in this lecture, we will be dealing with tensor derivative operators that are mainly calculus operators such as gradient, divergence, Laplacian and curl. And we will also look into the tensorial form of the Gauss's theorem and Stark's theorem. This is an overall idea about what we are going to discuss in this lecture. In this lecture, we are going to look if a gradient acts upon a scalar or a divergence or any operation or any function acts upon a scalar, vector or tensor, what will be the resultant and how it is expressed in terms of Einstein's notation. Therefore, just look into our first operator, that is gradient. When gradient is acted upon a tensor scalar, we can see that we are much familiar with these equations and we have done this in our elementary classes. Just have to note how this is being expressed in terms of Einstein's notation. It's just an extension of what we have learned so far. So we know in gradient, when a gradient acts upon a scalar, it will produce a vector. We have done this so far. So this is expressed in terms of Einstein notations as when gradient operator del is acted upon a scalar psi, the action is such as dou by dou xi is acting upon the psi, and we will get a vector such that dou by dou xi of psi is equal to xei. Therefore, this has an operator. See here we have only one. See here we have only one index. Therefore, this is a free index. If this is a free index, then we will have such terms, 3 or n such terms, n such expressions. So this will be a vector, and here this term will be in the direction of ei. And when a gradient acts upon a vector, when a gradient acting upon a vector, gradient is dou by dou xj acting upon a vector, the vector component vi. So when a gradient acts upon a vector, it will produce a tensor. We are familiar with the gradient acting upon a scalar, but here we have to also study about when a gradient acting upon a vector. See, this will produce a dyad. Here we have the dyad tensor product of ei and ej. We know that when two vectors come together to form a tensor product, then the result will be a tensor. A dyad of two vectors is a tensor. Here the operation is dyad. Operation is not dot product, not cross product, but the operation is dyad. Therefore, two vector on dyad operation will produce a tensor. And here the derivation of vi is happened with respect to vj. Therefore, instead of having one a free index, here we have two free indices. If we have two free indices, then the resultant will be a tensor. In the previous sense, we have only one free index and the resultant was a vector. Here we have two free indices, therefore the resultant is a tensor. Now let us look into another function, that is divergence. So divergence, when this function acts upon a vector, that is divergence of a vector, will produce a scalar. Let's see how. Del dot v acting will be written in tensorial notation as dou by dou xi on vi. See, here we have two i's, and therefore these two i's acts as dummy indices and we have no free index. Since we have no free index, this will produce a combination of linear combination of some terms a plus b plus etc., and the answer will be a scalar. We have two dummy indices over here. So when a vector, a divergence is acted upon a vector, here we come across a contraction. We have already seen what a contraction is. That is, we reduce to certain ranks of the material. So here the vector is reduced by a rank, and here we get a scalar. Similarly, when divergence acts upon a tensor also, here we have one free index and one dummy index. Therefore, since it has one free index, it will result in a vector. Here the vector is in the EI direction. Therefore, when divergence acts upon a tensor, the answer will be a vector. Here also we have contraction of one term, and this also leads to contraction of at least one term. So the next operation is curl. We already know how curl acts upon a vector. We know that when curl acts upon a vector, the resultant will be a vector. Therefore, this is denoted in tensor notation. We have already seen this denotation in one of our previous videos. We know that U cross V will result in epsilon ijk ui vj in the direction of ek. Correct? When it is, therefore, this will give you the kth component of this will be epsilon ijk ui vj ek. We can also get rid of ek when we are directly writing in the Einstein notation. So the answer will be epsilon ijk ui vj. Here, just that the u is replaced by another product, that is dou by dou xj. Therefore, we have epsilon I jk vi epsilon vjk in the direction of ek, or if in the direction of ei, then it is dou by dou x vk divided by dou by dou xj of vk. So this will result in a vector. See, here we have one free index. Therefore, it will result in a vector. And when a curl acts upon a tensor, similarly it will result in a tensor because we have two free indices. Therefore, it will result in a tensor. And the Laplacian operator. Laplacian is a combination of divergence as well as gradient. Here in the previous examples, see, when a gradient acts upon an element, its rank is increased by 1. That is, when it is acting upon a scalar, it will produce a vector. When it is acting upon a vector, it will produce a tensor. Similarly, when divergence acting on an element, it will reduce the element's rank by 1. That is, when it is acting upon a vector, it will produce a scalar. It will acting upon a tensor produces a vector. Therefore, Laplacian is divergence of gradient of any scalar product. Therefore, we know that a scalar acted upon by a gradient will produce a vector, and a vector on operated with a divergence will produce a scalar. Therefore, the Laplacian of any scalar quantity will be a scalar. So, therefore, this is divergence of gradient of psi. So, we will have two different products over here. That is dou square psi. First, we will take the divergence. So, it will be dou psi by dou xi. Then, it will be acted upon by the divergence operator. That is dou square by dou xi. For the purpose of solving problems, listen, when we have to act upon by a gradient, we know that it have to be elevated to a rank of 1. Therefore, if we are acting on an element vi, if a gradient is acting on a component vi, then the gradient have to be of the index other than I. Then only we will get two free indices. But in the case of divergence, See, if it is acting on a component I, then the operator, the partial derivative operator, should also be of the index I. Then only we will get a contraction, the delta here. Then only we will get a scalar. Therefore, for the purpose of solving problems, see that if it is gradient, take a index which is not the same as the component. But in the case of divergence, take an index which is same as that of the component. Now we have to learn how these things are related in our tensor analysis in the base of tensors, what we have learned so far. So a gradient of a scalar, we know that the gradient of a scalar will produce a vector. Therefore, gradient of a scalar psi in any generalized coordinate system, say Riemann manifold, we can write it in terms of the generalized coordinate qi as del psi is equal to del operator can be as dou by dou qi, which is written in the generalized coordinate basis vector epsilon I. We know that epsilon I can be written as a linear combination of our orthonormal coordinate system x as dou by dou xk of ui. Therefore, substituting this over here, we will get a tensor multiplied by dou xqi. We know that this is a vector and this is a tensor. Since a vector can be mapped by a tensor to another vector, this quantity over here must be a vector. Therefore, gradient of a scalar is a vector. Similarly, we can look into how the gradient of on a vector acts. We know that vector in generalized coordinate system can be transformed into a normal coordinate system using this transformation equation. We have done this so far. Since this is a contravariant vector v, then that's why the transformation equation is like this. Now we act upon this new tensor with respect to the new coordinate system. Derivative is taken with respect to the new coordinate system, dou by dou qg. Now this will give us a tensor, and another will also, this operation will also give us a tensor. Therefore, using the quotient rule, we can say that this quantity over here must be a tensor of rank 2. Therefore, gradient of a vector is a tensor of rank 2 and gradient of a scalar is a tensor of rank 1, that is a vector. Now let's do a small problem, that is gradient of phi psi. We know that gradient of a phi psi, that is del of phi psi. We can just take the partial derivatives, dou by dou xi. Here the index doesn't matter because these are just scalars. So phi psi, using chain rule, we can write that phi dou by dou xi of psi plus psi into dou by dou xi of phi. Therefore, the answer will be phi into gradient of psi plus psi into gradient of phi. Now let's look into what is meant by divergence in terms of tensor analysis. We know that divergence is taking a contraction. That is, we are contracted the element by a term 1. Therefore, in divergence, what we do is the partial derivative is replaced by the covariant derivative. The partial derivative is dou by dou qi, while the covariant derivative have another term which depends on the second kind Christoffel symbols. Therefore, the divergence of a vector can be written as the covariant derivative of that vector. Here see that the the derivative is taken with respect to the same index. Therefore, instead of writing Vij, we write Vii in case of this covariant derivative. Therefore, the covariant derivative Vii epsilon I, or by dropping epsilon I, we can write it as covariant derivative Vii. We know that we know expression for covariant derivative. If the covariant derivative of Vji, we can write it as dou by dou Qjvi plus Vk into Christopher symbol gamma jki. Here we have both the integers as same, so we can replace all the j's with I and write it in this term as partial derivative of Vi plus Vk into gamma iki. We know the expression for gamma, the Christopher symbol of second kind, can be written as a partial derivative of the metric tensor. Therefore, we can write it in this combination. We know this equation, we have derived it. So, by replacing Rs with I, we can write this equation can be written in this form. We know how to expand this equation in terms of Christopher symbols of first kind, and we know that some of the terms over here will cancel out. Here you can see, hope you remember how we have expanded it. For example, this term over here can be expanded as Ik n into nki. Similarly goes this term, but see in this term we have k and I replacing with each other. So the terms over here, both the terms over here, the four terms over here will cancel out, because it is okay to replace k and m in Christopher symbols, in metric tensor. And also when computing the Christopher symbols of first kind, all the four terms over here, that is this and this quantity, will cancel out, and the remaining portion is just half gim dou by dou qk of gim. Please do it on your own and see this cancels out. Okay. See, we have a term over here. But we are similar with this kind of an expressions in our metric analysis, in our course in metric analysis. See, this is a vector which is written as A inverse. If GIM, this term can be denoted as a metric A, then this GIM should be A inverse. So what we have is here A inverse, some scalar into A inverse into dou by, that is a derivative dou by dou x or dou by dou q into A. And we are similar with this kind of an expression. This kind of an expression comes in the theory of derivatives. That is, we can take the derivative of a determinant of a vector such that the derivative of determinant of a vector is equal to, determinant of a matrix is equal to determinant of that matrix into summation over A inverse Ij into derivative of all its components. Now, this is similar to what we have here. Therefore, we can rearrange this and write. So, this can be replaced with 1 by derivative of A into this term divided by, we have a scalar here, that is 1 by 2. Therefore, this Christopher symbol gamma iki can be written in this form. And this form over here, our computation, we will get as 1 by this is G stands for determinant of G. Determinant of G half into determinant of G half raised to half, that is root over determinant of G into dou by dou QK into root over determinant of G. Therefore, the whole product del dot V. We know that del dot V can be written in this form. So we have found what is this, and what we have left is a derivative of this and a free index of this. Therefore, bringing this into a derivative, this is of the form some product into derivative of Vi plus V into derivative of something. Therefore, we can take this whole product into one such derivative, and therefore Vi is taken into one derivative, and del dot V can be expressed in this term. Since G here is matrix tensor, and we know that the metric tensor in an orthogonal system is a diagonal tensor with we have h parameters in all its diagonals. Therefore, determinant of G will be the product of its diagonals. Therefore, we can replace the kth component of this expression as written in this form. Therefore, see, we have no free integers. Here we have only dummy integers. Therefore, no free integers are available. Therefore, the answer for here goes to a scalar. So, let's do a problem. Derivative of phi into f. We know that derivative is del dot phi f. So, we have to first determine for what index it is being denoted to, because here we have a vector. So, let's say I am writing for the index I. If I am writing the derivative for the index I, this notation over here, del should also be dou by dou xi, because we are taking a derivative and we need a contraction. Therefore, the answer here will be, what we have is dou by dou xi into phi of fi. Therefore, it can be written as phi into dou by dou xi into fi. See, here are no free integers. Therefore, this will produce a scalar plus f into dou by dou xi of phi. See, here we have one free index, so this term is a vector, and this is dotted with another vector fi itself. So the ith product, then this will produce a scalar, and this scalar is added with a scalar, and the answer here will give you a scalar. Therefore, the answer here is phi into divergence of f plus f dot gradient of phi. Now let us look into the curl operator. You know how to take a curl operator. We have seen this so far. So instead of taking u cross v, you will just replace this with del operator, and del cross v will give you the curl of v, and all the other tensorial notation including the Levi-Civita symbol and all the other terms will remain as the same. So in a curl operator, when you are doing it in the matrix formation, you know that we have to take the products over here. That is, you will have all the partial derivatives in your second term and all the components in your third row. Therefore, what you are taking is dou by dou xi by vj, dou by dou xj by vk. So actually you have to take a combination of this partial derivatives. So the combination of the partial derivatives are dou by dou qj into vi minus dou by dou qj into dou by dou qi into vg. See, this term notation here can be adjusted using the symmetry of the Christopher symbols by adding and subtracting with Christopher symbols. Therefore, we have added a Christopher symbol. We can add and subtract two Christopher symbols. Therefore, these can be clubbed together to write the covariant derivative of Vij, and these can be clubbed together to write the covariant derivative of Vji. We know that inside the Christopher symbol, replacing I and j do not make much difference. Therefore, this can be used by writing the symmetry of the Christopher symbol. Therefore, the characteristic difference of these derivatives actually comes to be the covariant derivative of the vector. Since we know that the covariant derivative is a second rank tensor, the answer here must also be a second rank covariant tensor. Now let us try to prove this equation. That is, gradient of two vectors f dot g should be written as f cross curl of g plus g cross curl of f plus f dot divergence of g plus g dot divergence of f. So as a first step, we know that gradient of f dot g. So gradient here, this is two vector terms. We have to first choose on what index it is being, it should be acted upon to. Therefore, let us choose the ith term. Therefore, we can write the first term as gradient is taken over fi gi. So fi gi here becomes a scalar. Now, when gradient acts upon a scalar, we know that the answer should be a tensor. Therefore, the gradient should take another index, say xp. So, the derivative is taken with respect to xp on fi gi. As we have done, we know that it will be fi into dou by dou xp of gi plus gi into dou by dou xp of fi. Now let us move on to the next term, that is f cross curl of g. So here we have a cross term. Consider curl of g as one single function. What we have here is of the term a cross b, is of the form a cross b. When we have a cross b, we know that it can be written as epsilon I j k. That is the kth term of epsilon. This term can be written as epsilon I j k fi into the another function. Another function here turns out to be curl g, the jth component of curl g. Here the kth component of f cross curl g can be written as Levi-Civita symbol ijk fi into the next function j. Now it is in the direction ek. We can drop ek in terms of Einstein notation. So here we have come with this symbol. Now we have to look into the curl g. So curl g also gives us a cross product. Now the first term is dou by dou x of something into g, which is in the jth term. Therefore, the jth component here, Levi-Civita symbol ijk into fi. Up to this, it remains the same. Now we have to write it for the jth component. Therefore, the third Levi-Civita symbol will be J, and we can replace it with two other forms, say P and Q. Okay, P and Q. Now we have curl. Now curl, the first term should have this index. So dou by dou xp in the second term, that is G, carries a symbol Q. Now I can just write epsilon I j k into epsilon P Q J Fi into dou GQ by dou XP. Please don't get confused when I lower or upper the index. Is just a matter of matrix notation. You know you can do that. Since I haven't actually said you what this vector is, a covariant or contravariant, and you know you can just change covariant and contravariant by just using metric tensor. So here I have a combination of two Levi-Civita symbol. In the case of Levi-Civita symbol, we have an identity such that Levi-Civita symbol ijk with PQR can be written as delta IP into delta JQ minus delta IQ into delta JP. Therefore, just ignoring the last two integers, these integers are taken in the form IP, first to first, IP JQ, and in the next term it is taken as IQ and JP. So, this can be written in that format. But the term which can be avoided is the jth term, because all the other term I, P and Q comes over this term. So the term which can be avoided is jth term. If the jth term have to be avoided, it have to be the third index. Therefore, I am just replacing this J and K. If I switch J and K, we know that in case of Levi-Civita symbol, it will give you a negative sign, because IJK goes in a cyclic order, but in the case of IKJ, it will go in a reverse cyclic order. So this will give you a negative sign. So this can be written as negative of epsilon IKJ into epsilon PQJ, and the other terms are just fine, Fi into dou GQ divided by dou XP. Now, this can be expanded using this relation, and I can write it as minus of delta IP into delta KQ minus delta IQ into delta KP into Fi dou GQ divided by dou XP. Now I can just use it over here. So using it, we know that when delta I have to be equal to P, therefore I and P can be identified. I can write it as minus of Fi into dou GQ divided by dou Xi. Similarly, using the second term, I and Q can be identified. Therefore, the term becomes Fi into dou Gi divided by dou Xp. Now, here an ith term dotted with ith term of something. So what will you get this? You will get it as f dot del g. That is, you will get it as f dot del g. We have a minus sign here, and plus of fi dot dou gi by dou xp. Now this is for f cross curl g. Similarly, we can write a similar equation for g cross curl of f. This will also give you a similar equation, that is f dot del g, this will give you minus of g dot del f plus gi into dou fi by dou xp. Now we have these terms fi into dou gi by dou xp and gi into dou by dou xp of fi. So we can substitute for these two values from these two equations, and we can write that the result gradient of f dot g is equal to, instead of first simple, we can write it as the product over here is f cross curl g. Therefore, it is f cross curl g plus this symbol, that is f dot del g. Similarly, using this, we can write it as plus g cross curl f plus g dot del f. I know that this is pretty confusing in case of index notation, but you can practice it. You have many practice questions in your text of H.K. Das. I recommend you to practice as many questions as possible. There are many solved examples in that in that textbook also. And if you come across some problems, you can just text me. Now the last operator, that is a Laplacian. We know that Laplacian is nothing but del of del psi, that is divergence of gradient of a scalar. We have seen that divergence of something, that is del dot v, can be written using the matrix notation and the Christopher symbol in this form. Therefore, what we need to do is just to replace this vector v with del f, that is dou by dou xi or dou by dou qi of this symbol. So this is what is being written here. Just v is replaced by dou qi of psi. Therefore, dou by dou qi comes over here. Psi goes over there. And we can see that these symbols over here. This give you the covariant coefficients of del square psi. In an orthogonal system, we know that the metric tensor is diagonal and its diagonal elements are the h parameters. Therefore, this root over g can be replaced by h1, h2, h3, and we can write this in this format. And you can see that this will give you a scalar. So let's do one more problem, that is curl of gradient of phi, and we have to prove that this is equal to 0. So let's start. Curl of gradient of phi. So curl, say del cross gradient of phi, I wish to take dou by dou xi of phi. So curl of something, since it is xi, that is ith component of psi, I have to take I as the second index. So I take dou xj, I comes second, and whichever in the direction, if it is taken in the direction of I, in the direction of k, the k goes last. And the first term, that is del will carry a coefficient, an index j. So it is dou by dou xj into what I have here as dou by dou xi of phi. So I can write this as epsilon j I k dou square phi divided by dou xj into dou xi. And let me call it as I. And I can, since see I and j here repeat twice, so I and j are dummy indices. We know that we can replace dummy indices. So by replacing dummy indices, I and j, I can switch I and j and write this equation as epsilon I j k dou square phi divided by dou xi into dou xj. And this is also equal to I. Now you will be confused why I didn't change the sign over here. I didn't change the sign over here because I was just replacing my dummy indices, and this replacement has taken over all the terms. This replacement has done over all the terms. So here this sign change does not occur. Now let me add these two terms, these I and I. So what I have here is 2i is equal to epsilon j I k into dou square phi divided by dou xj into dou xi plus epsilon I j k into dou square phi divided by dou xi into dou xj. Now I can replace these two symbols by switching over here, not by switching the indices, not by switching the dummy indices, just having a rearrangement inside the Levi-Civita symbol. So this will give me a negative sign of negative ijk into something plus ijk into something. And we know this while we are learning our complex analysis. We know that homogeneous equations, since homogeneous, these terms are equal. That is dou square phi by dou xj into dou xi, or taken derivative in the other form, that is xi and then xj will give you the same result. So the products over here are actually the same. Therefore, this turns out to be 0. Since this turns out to be 0, I is 0, which means that the curl of gradient of a scalar is 0. Now, we have to find the tensorial form of the Gauss's divergence theorem. You are well versed with Gauss's divergence theorem. This theorem states that when the flux of a vector inside a closed surface is equal to the divergence of the field inside the volume. So this theorem actually does is it relates the change in the flux inside a volume, that is it will find the new sources and sinks, and it says that the net change in the flux will be that field which is going out of the volume in normal direction through all its surfaces. Therefore, this can be written in mathematical form as when V is subset of Rn, that is considering volume is a subset of a real space having n dimension, which is compact, and also it has a smooth symmetry S, smooth boundary S. Then if f is a continuously differentiable vector inside that V or in the neighborhood of V, then we can write the volume integral of del dot f. Del dot f is divergence of the function. Divergence of the function tells us how much it is varied inside. That is, does it have any sink or does it have any sources? If it doesn't have any sink or the sources, the divergence is going to be 0 because there is no diverging inside the vector field. The net coming inside and net what is going outside will be the same. If there are sinks and sources inside that volume, the divergence is going to stand. Therefore, it is del dot f inside the volume dV will be same as what is going through the surfaces in normal direction. Therefore, along the closed surface f dot n ds. So, in tensorial form, we can just replace, since it is divergence, we can replace the fi can be partially differentiated with dou by dou xi of dy, and also since it's a dot product, we can say it as fi ni. All is written for the index I. So this is the tensorial form using the Einstein notation. And also if it is not a vector but a tensor, we can write the same for the tensor also. And the tensor may have rank from I to Z, and it is differentiated with dou by dou xi. See, this is the divergence which we are playing with. So if it is a divergence of an element, it will reduce the rank. That is, we will come across a contraction. Therefore, there is a contraction occurring on the sides. Therefore, this simple over here or the term over here will become a scalar. Similarly, the term over here will have a reduced rank of 1. So we have a contraction over here. Similarly, in case of Stokes theorem, you know that Stokes theorem says that in a given field, we can relate the integral of the curl of a vector field over some surface to the line integral of the vector field along its boundary. That is, line integral of a vector field over a loop is equal to the curl inside that surface. And here the surface we are considered as sigma. Sigma is a smooth oriented surface in the real space with dimension 3, and its boundary is taken to be delta sigma. If A is the vector field which is defined and has continuous first order partial differentials, then using Stokes theorem, I can write that the surface integral of del cross A into dA will be equal to the line integral, closed line integral of A dot dl along the contour delta sigma. Therefore, in tensorial notation, since it is a cross product, I can write it as epsilon ijk dou by dou ak xj in the direction ei, and it is written for the ith format. Here also, since it is a cross product, we cannot have contraction of the indices. So, in this lecture, what we have seen is just an extension on how we can use this derivative operator over our tensors and vectors, and these are my references. Kindly I request you to go through the examples and exercises, especially in the text of H.K. Das and Ramavarma, because it have got many beautiful examples, and you can practice over this notations, especially which is including this Levi-Civita symbol and its connection with the Kronecker delta. Similarly, you can use this divergence notation. We know that divergence notation in a general coordinate system is what we have discussed. You can just elaborate that into your non-coordinate system such as Cartesian, polar or cylindrical, and see if gives you the right results. So thank you.